Hey everyone, this is Kenny.
This is Mike.
Coming in live. Season's greetings, Bill. Hope you have your popcorn and butter ready, my friend. We're gonna explain part A first by walking you through how we solve the biochemical oxygen demand differential equation, which we're just gonna call BOD, using Euler's method, predictor corrector, Runge-Kutta, and desolve.
We will then take you through part B by walking you through how we solve the dissolved oxygen, which we will call DO, this differential equation by using the Euler method, predictor corrector method, and desolve.
So for starters, BOD is the amount of dissolved oxygen needed by anaerobic biological organisms to break down organic material in a body of water. And the rate of the change of the oxygen equivalent remaining organic matter can be described as a differential equation. The time derivative of L equals the negative deoxygenation rate constant, which is 0.55 per day, times the oxygen equivalent measured in milligrams per liter.
We are asked to solve the BOD problem for a water body for a total time of 6 days with time interval dt equaling to 0.5 days using the Euler method, the predictor corrector, Runge-Kutta, and desolve. We are also told that the initial BOD is 15 milligrams per liter.
Alright, so here's the Euler method script. We used a for loop to implement the Euler method. The time vector is from 0 to 6 days with 0.5 day increments. Here is the graph from the previous slide script. As you can see, as time goes on, the oxygen equivalent of the organic chemicals remaining decreases.
Alright, now we'll move on to the predictor corrector method. Here we have the script for this method. We also use a for loop in this script as well. Next we'll move on to the graph. It looks similar to the Euler method. As previously stated, when time equals 0, L is 15 milligrams per liter.
Alright, let's move on to the Runge-Kutta method. This is the fourth order Runge-Kutta, which is a built-in MATLAB function. It's called ODE45, but we thought it should be renamed Colt45, which has been the obvious theme of this part so far. Let's move on to the graph. The graph is also similar to both the Euler and predictor corrector method ones. Again, as time goes on, the oxygen equivalent of the organic chemicals remaining decreases.
So now let's take you on to the next method, which is called desolve.
Desolve!
Through this script, we ran the built-in function desolve. Then we use subs to input our time interval. As we look at the graph, this is again what we expected. It follows in a similar trend to the graphs before it.
Alright, so here is the graphs of all of them put on top of each other. As you can see, the Euler in red is slightly lower than the other three methods. And then lastly, for part A, we will clearly mark what the oxygen equivalent concentration is after 1.5 days. Alright, Bill, we thought we'd shift gears just a little bit. We're going to take the baseline for a walk and keep the cymbals splashy. We're going to serenade your eardrums with a little Yaz flute, my friend.
Alright, but now onto the material. The rate of change of dissolved oxygen that we call DO in water can be described as a function of the rate of change of oxygen consumption by organic matter and the rate of change of oxygen addition through aeration. The equation for DO concentration is shown here. The constant DOS is the amount of dissolved oxygen at saturation, which in this case is equal to 9.17 milligrams per liter at 20 degrees Celsius. K sub R is the reaeration coefficient, which is equal to 0.45 per day. And then M in this case is the relaxation index.
So we'll now take you into the results for the Euler method and predictor corrector method for M equals 0.75 and 1.25, and then desolve where M equals 1. So this is the Euler method where M equals 0.75. Here we for loop the BOD equation as well as the DO. As you can see, M equals 0.75, and the graph for this kind of looks like this. The trend line increases by a lot for the first few days, then tapers off and begins to decline midway through at roughly 50 milligrams per liter of DO.
Alright, so now we move on to the Euler method, the second version of where M equals 1.25. Here we have the same script as the first one, except m equals 1.25 instead, like I said. So in the graph, we can see that there is a significant difference by simply changing the value for m. There's a steep increase through the first half day, and then decreases after day 1.
Alright, so let's take it to the predictor corrector method. Through the predictor corrector method, we solve for the DO concentration for m equals 0.75. The graph has a smooth curve that gradually decreases after the third day.
Here we move on to the predictor corrector method for m equals 1.25. It's similar to the same script as in the previous two sides, except we changed the value for m. Alright, so now we move on to the graph for this method. This graph, however, has the same change the Euler method had. It shoots up at a high rate and morphs the shape of the Euler method for m equals 1.25, as you can see in the next slide. As you can see here, there's a significant comparison in both of them, at where m equals 1.25.
Alright, let's move on to the desolve.
Desolve!
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 Alright, now onto the graph. Alright, so here we clearly marked when DO is lowest. It occurs after 1.5 days with a concentration of 5.2264 milligrams per liter. Alright, so in conclusion, that's all for this presentation. Hope you enjoyed it, Bill. This is Kenny.
This is Mike.
We're signing off. Desolve!
You play jazz flute?
I dabble.
Would everyone love to hear Ron Burgundy play some jazz flute? Yes! Please. You, get on stage now.
Okay, I guess I can play a little ditty. Honestly,
Come on. Give him a hand.
I'm not prepared. I really am not prepared at all.
Yes!
This is a surprise, tell me.
Guys, East Harlem Shakedown, E flat. Keep the cymbals splashy, and Jerry, let's take the bass line for a walk. Hold on. I'm not hearing it right. Hold on. We got it now. It's all right. Little ham and eggs coming at you. Hold on, people. Hope you got your griddles. That's baby making music. That's what that is. Let's go.